In this video, we take a look at review problem 3.10. X is uniformly distributed with parameters 0 and 1. Y is exponentially distributed with parameter 1, and these are independent. Find the PDFs of these two quotients. First, where z is equal to y divided by x, and then w, which is equal to x divided by y. To get started with this, we first write down the PDFs for the two random variables. So the first one is uniform between 0 and 1. And so the PDF is simply equal to 1 as long as x is between 0 and 1. And next we have the PDF for y. And that's going to be e to the minus y as long as y is greater than 0. So that's our formulas. First off, let's get the PDF for z, which is equal to y divided by x. And the formula goes that the PDF for z evaluated at the point z is equal to the integral from minus infinity to infinity of absolute value of x times the PDF of x times the PDF of y evaluated at x times z, and I integrate dx. Now for this problem, the PDF only takes values when x is between 0 and 1. So for this part here to be anything other than 0, x has to be between 0 and 1. If x is between 0 and 1, then the absolute value of x is equal to x. And then I evaluate the PDF at y, evaluated x times z. So if it's e to the negative y, here I'll have e to the negative x times z dx. And then everything else is simply calculus to figure out the value of this integral. And when I compute this integral, it will be a function of z because the left-hand side is a function of z. Okay, so to do this integral, we have integral from 0 to 1. Let me write this as x over z times z times e to the minus x times z dx. So introducing an extra z here and here. And the reason I do that is so that I can integrate by parts. So x over z times negative e to the minus x z prime dx. And so integrating by parts, we get negative x over z, e to the minus xz, evaluated from 1 to 0. Then minus a minus becomes plus, integral from 0 to 1. The derivative of this with respect to x is 1 over z, times the antiderivative, e to the minus xz, and the minus sign here got absorbed in the minus sign here, dx. So computing this, we get negative x over z, e to the minus xz. I'm going to let that carry along for the ride. Computing this integral, we get minus 1 over z squared, e to the minus x times z. And I evaluate between 1 and 0. Plugging in 1, we get, and I'm plugging 1 for x, not for z. Plugging in 1, we get negative 1 over z, e to the minus 1 times z, minus 1 over z squared, e to the minus 1 times z. Then plugging in 0 for x, we get 0 times whatever is 0, minus 1 over z squared times e to the 0, which is 1. And so simplifying, we get that everything's over z squared. I can have a minus becomes plus 1. If I put z squared in the denominator, the numerator here becomes minus z times e to the minus z. And then this numerator becomes e to the minus z. So there's my PDF. 1 minus z e to the minus z minus e to the minus z over z squared. And this is true for any positive value of z. So that is the PDF for this one. It turns out if you integrate this one from 0 to infinity, you do get 1. Now let's turn to the second part of the problem, where I have to do the same thing, except this time I reverse the role of which one's in the numerator and which one's in the denominator. So my formula this time is going to look a lot like what I had before. Let me write down the PDFs again. The PDF for x is equal to 1 as long as x is between 0 and 1. And the PDF for y is equal to e to the minus y as long as y is greater than 0. Now interchanging the roles of x and y in my integral, the PDF for this quotient, and I'll put this in terms of w this time instead of z. Same formula, integral from minus infinity to infinity, absolute value of absolute value of x, times the PDF of y evaluated at point x times the PDF of x evaluated at x times z dx, where I've switched the roles of x and y here. Okay, now first things first, let's take a look at the PDF for y. The PDF for y only turns on when y is greater than 0. So the thing inside the parentheses here must be greater than 0. So I can write this as integral from 0 to infinity for now of this part here is e to the minus x. If x is greater than 0, then the absolute value of x is x again, so that's simple, times the PDF for x. Now the PDF for x is here, so I need to have the thing inside the parentheses must be between 0 and 1, which means that x must take values between 0 and 1 over z. So this is integral from 0 to 1 over z of x times e to the minus x times 1 dx. And so this is my different integral I get for, because I have a different numerator and denominator here. Okay, now this one again I do by integration by parts, and this one's actually easier to integrate because there are no z's embedded inside here. So integrating this by parts, we get negative x e to the minus x evaluated from 1 over z to 0. Then minus minus becomes plus, integral from 0 to 1 over z. The derivative of x is 1 e to the minus x dx. Computing this integral, we get this part comes along for the ride. Computing this integral, we get minus e to the minus x, and I evaluate this between 1 over z and 0. And so plugging in, if I plug in x equals 1 over z, I get negative 1 over z, e to the minus 1 over z. Plugging x is 1 over z, I get e to the minus 1 over z again. Plugging in 0, this part is clearly 0. Plugging in 0, e to the minus 0 is 1. And so I end up with 1 minus e to the minus 1 over z, 1 plus 1 over z, and the quotient again can be any positive number. And so that's the PDF. Just to give you a taste of what these functions look like, I plotted these out. So the PDF, the first PDF I got is going to be this curve here, and let me just highlight that. This one here that I'm tracing over now, that is the first PDF for y divided by x, and the area under that black curve is equal to 1. The second one that I got, 1 minus e to the minus 1 over z times 1 plus 1 over z, that's this first curve. And if we take a look at it, we see we have this, there's a very real possibility. It comes in almost horizontal, actually it does come in horizontal here at 0. And we see that it's more likely for the quotient x divided by y to be close to 0. There's a lot more area close to 0 under the top curve than under the bottom curve, which represents y divided by x. Now that makes sense because y is exponential, and so y could be a very large number, which means x divided by y could be a very small number. So it makes, as opposed to this one, y is exponential, x is between 0 and 1, so because I'm dividing by something that's between 0 and 1, that will have the effect of of multiplying something by y that's greater than 1. So these are the two different curves. They are both PDFs. The areas under both curves are equal to 1.